Hello, welcome everyone to this session of the Gamma seminar. Sorry for the delay, we had some technical issues. Today's speaker is Javier de Lucas from the University of Warsaw and will give the last lecture of his course on Lie systems and compatible geometric structures.
So, welcome back. I apologize for the delay. I had to buy a new computer because the last one had more than 10 years and I had to configure everything to work. So let us continue today with the talks about Lie systems. And in this talk, we will talk about Lie systems with compatible structures. Let us say that this is the most recent trend in the study of Lie systems, and it's very interesting because it mixes differential geometry, integrable systems, and of course the theory of Lie systems. And you can use this for studying numerically differential equations, certain technical problems, and a lot of stuff. And also it makes things easier. This is the main point of using geometric structures to study Lie systems. And the thing is that you will have powerful tools to obtain superposition rule, integrals of motion, and other properties of Lie system that otherwise should be obtained by means of solving a system of differential equations, partial differential equation, ordinary differential equation, which is pretty much easier. Also, from the mathematical point of view, is more beautiful to use geometric structures. So I will start with the typical example of a Lie system with a compatible differential equation. Okay, and the initial example we found was around 10 years ago, even more, 15 years ago, maybe even. The first example was concerned with the Riccati equation. It was concerned with describing the superposition rule for Riccati equation. During my PhD, it was known how to obtain it by means of solving a certain system of differential equations, and it was pretty much difficult to do it. So let us recall that we start by means of a certain differential equation on the real line with time-dependent coefficients. Let us recall that we don't know an analytic solution for Riccati equation with the coefficients A1, A2, and A3 of t. Sorry, this should be A3. Okay, this thing, A3. We don't know how to solve it. So a superposition rule allows you to obtain the general solution out of three particular solutions of this differential equation, and you could, for example, obtain them by means of numerical methods. So you cannot know one of these solutions. So the standard way to study this geometrically, it was to relate the right-hand side of the Riccati equation with a time-dependent vector field. I mean, a t-parameter family of standard vector field. So the way is, yes, to put this as a vector field on the real line, okay, of this way. And you see, the only thing you have to do, and this is A3, as I said before, the way of doing this is just to consider for the right-hand side this part like the coefficient of a time-dependent vector field. Okay, so remember that by the Lie theorem, it was stated that the Riccati equation would be a Lie system. I mean, it will have a superposition rule if this time-dependent vector field can be written as a linear combination with time-dependent coefficients of vector fields closing a Lie algebra vector fields, finite-dimensional Lie algebra. And you see, this time-dependent one is attached to this vector field, this second function with this third, and this third time-dependent function with this third vector field. So you have three vector fields in here. And if you make the commutators of this vector field, let me recall you that you will obtain that this is just this. So the first with the second is the first with the third, it will be twice the second, and the second with the third, it will be just the third. So as you see, the Lie bracket of two elements of this Lie algebra gives you some element of this Lie algebra with standard coefficients, with constant coefficients. So it's a Lie algebra. And I recall you that from previous talks, the way of working out the superposition rule was by working out the diagonal prolongations of these vector fields to third-time copies of the first manifold. You see that here, this thing, this part in here, is the diagonal prolongation of this vector field to R4, because you see, you have here 4 pieces for A equal to 0, 1, 2, 3, and each one of these is just this vector field, but defining another manifold. And this thing in here is just the prolongation to R4 of this vector field. It's the same. Each piece of this is exactly this vector field written with another coordinate corresponding to each copy of R on R4. And the same applies to this. And the theory of this system tells you that to obtain the superposition rule, what you have to do is to obtain a third-time solution, a third-time function in this case, third-time set of functions that are common integrals of motion for the diagonal prolongations of the vector fields of the Bézier-Goubel algebra. There were some technical conditions to establish how many copies of the initial manifold you have to have. Yeah, but the main point to what follows is that for this vector field, for this vector field, and for this vector field, you have to obtain psi. Okay, and this psi is just a third-time constant of motion. Okay, of these 3 vector fields. You can imagine that if you should solve this system of PDEs by yourself, that would be very difficult to do. Indeed, it takes a while, quite a long while to do it. And Lie did it, Sophus Lie did it. And it turns out that you can find one particular solution that is this thing, okay? This thing in here is you put here, this here, this here, this here, and it turns out that this is a constant of motion, the first field of the second and not the third. And to obtain the superposition rule, what you do is just when you have this constant of motion, you suppose that this is a 13 constant k, and you write one of the variables x0 in terms of the other one. And this, what you obtain is just the superposition rule. Yeah, so this is indeed, this is a subindex, sorry. So this is the way of obtaining a superposition rule. But the main point in here, the difficult point to obtain, is just to obtain this. And also there is another thing, is that this thing, this psi, is a non-invariant in projective geometry. So somehow it turns out that this constant of motion that is appearing here, that you have during the 20th century you had to obtain by solving a system of PDEs, somehow it has some geometry, and somehow maybe you can find a way to obtain it without solving a PDE by brute force. So this is done by means of geometric structures. When you try to solve this system of PDEs here, the theory of Lie systems, the Lie-Hamilton systems, that Lie system related to a symplectic structure, allow you to obtain psi in a nice, cool way. Very elegant, very easy, very geometric, very, at the end, useful. So the thing is, the way of doing this would be by means of symplectic geometry. I will explain in this talk a little bit about symplectic geometry, and I will explain how to use this symplectic geometry to study this Lie system. So yes, for the time being, let me tell you that this invariant psi, this solution of the system of PDEs, it will be something called a Casimir function, and it will be obtained by means of symplectic geometry. So let's go with it. Let me recall, for those who doesn't know it, what a symplectic manifold is, and 13 properties of symplectic manifold that are worth of studying. Okay, there are many of them that are very interesting. So the first thing is what a symplectic manifold is. A symplectic manifold is a pair consisting of a 13 manifold and a third-time symplectic form. Well, what is a symplectic form? It's a two form which is closed and which is non-degenerate. For those who don't know what is non-degenerate, it means exactly that if you had the omega, the symplectic form, okay, a differential two form is said to be non-degenerate if when these two form contract with a certain tangent vector and this is equal to 0, this is equivalent to say that this is x is equal to 0. This means non-degenerate. Okay. Essentially, it tells you that if you contract a two form, in this case, it will be non-degenerate if the contraction with a vector field is equal to 0, if and only if the vector field is equal to 0. This is what it's going to tell you. So this is a symplectic form, as I said, is a closed, non-degenerate two form. Okay. So it turned out that in general, when you have symplectic form, you can write it always locally around a generic point in a very easy manner by means of the so-called Darboux theorem. The Darboux theorem tells you that given a symplectic form on a manifold n, it means in an 13 open neighborhood of every point x, a coordinate system given by coordinates xi, pi, so that the differential form can be written in this way. Okay, so locally, absolutely all symplectic manifolds look the same way, in the sense that the symplectic form can be written in exactly the same way locally. Okay, so it is said that all symplectic manifolds look the same locally, because locally, up to a change of coordinates, there are 13 open subsets of a 13 manifold with a symplectic form given in this manner. These coordinates that allow you to write the symplectic form into this canonical manner given in here are called Darboux coordinate or canonical coordinates too. Okay, so the Darboux theorem tells you, okay, that you have always 13 locally n coordinates that play the role of configuration coordinates and 13 coordinates that play the role of 13 moments. Okay, 13 moments in classic, for example, like in classical mechanics. So this tells you that symplectic manifolds are always even dimensional because the number of these coordinates is even. This is one of the consequences of the theorem. Well, it can be proved other way, but it can be seen out of the Darboux theorem. So now there are more structures that are attached to 13 manifolds. I mean, when you have a 13 manifold in general, you will not have any symplectic form because, for example, if the manifold is all dimensional, a consequence, the Darboux theorem tells you that you will not have a symplectic form, because if you had one, it should take this form, and if it takes this form, the number of variables must be even. So symplectic geometry does exist only on even dimensional manifolds. And additionally, there are 13 kind of manifolds who naturally have a 13 symplectic form. So one of these manifolds which admits a symplectic form in a 13 canonical manner is the cotangent bundle to a manifold M. So how we do it? Well, consider a 13 point of a 13 cotangent manifold, and you can consider adapt coordinates to the cotangent manifold. I recall you that the way of writing adapted coordinates is that you pick up 13 coordinates xi on M. Okay, and now since you have the canonical projection from the cotangent to M, you can pull back these coordinates to coordinates on T star M. Okay, because xi is something that lives in M, so the pullback lives in here. Normally, it's a little bit misleading for students, but people used to write these coordinates in the same way as the base one. The only thing is that they define another manifold, okay, the cotangent. And once you have this, every differential form on M is something of this sort. F, something depends on X, the X. Well, you think that you have 13 coordinates xi, okay? So once you have this, or at every point x, this is just a certain cotangent vector, yeah, at every point of the M. So you can define 13 coordinates. Well, just let me write the indices in another manner, yes, to avoid confusion. Okay, sorry for that. Okay, so wait a second, this will be here. Okay, so you will define 13 functions of the cotangent that for a certain covector, they give you the coefficients. These are called the moment coordinates adapted to the cotangent bundle. So when you have adapted coordinates, they're coordinates of this sort. So the thing is, when you have these coordinates locally, you can define this differential form. But you see, you only can do it locally. I mean, you have a certain M, yeah, 30 manifold. You have a certain T star N that projects into M. So locally, you always pick up certain coordinates in here, and you leave them to the cotangent band. So you have this x, y, and here you have the x, y, p, y defined here. But you know, these coordinates are local. If you pick up another open subset of the manifold M, you will have another coordinates. For example, let us say that they are yi, and related to them, you will have another moments that will be pi I related to them. So if you construct these new, you could define in the same manner as here a new differential form. Okay, and you may wonder if this thing here and this thing here are exactly the same when the coordinates you use are defined, both of them. And it turns out that, yeah, I mean, if you make a change of variables from this pi I, yi to these variables, it turns out that this thing does not depend on the adaptive coordinate system. So it's a well-defined global object. It's well-defined, and due to that, you have defined a well-defined differential one form of the cotangent bundle. So this differential one form is usually called the canonical one form. It's also called the Liouville one form. It's also called the tautological one form. It has many names. And you can ask, what is the point of defining this thing? But we were talking about symplectic geometry, and symplectic geometry is about the symplectic form that is a two form, and this is just one form. So the thing is, if you differentiate this tautological one form, it turns out that when you add here a minus, you obtain this. And this is the local shape of every symplectic form in the manifold. That means that symplectic form, it turns out that you have proved that on every cotangent bundle, you will have always a certain symplectic form defined in a canonical way. More things. When you have symplectic manifold, you will define symplectic morphisms and things related to them. So a symplectomorphism is a diffeomorphism between symplectic manifolds. I've written here. You see, you have a 13 symplectic manifold M1 with a symplectic form omega 1. You have another manifold M2 with a symplectic form omega 2. And you will say that a certain diffeomorphism, and this is important to remember that this is a diffeomorphism, okay? So between these two manifolds is a symplectomorphism when the pullback of omega 2 is equal to omega 1. Yeah, so this is the relation. Also, this relation could be possible with something that is not diffeomorphism, that is non-invertible. But in differential geometry and symplectic geometry, we are concerned with manifolds that are diffeomorphism. Okay, so this is the thing. Okay, so what is the point now? The point now is that what we want to do with all this stuff is to describe Hamiltonian equations of motion in classical mechanics. Indeed, all this stuff came from the fact that during the 19th century, while studying the motion of planets, researchers Lagrange, Hamilton, Poincaré, and others came up with the idea of describing the Hamilton equation by means of some interesting geometric structures, by means of third-time bracket that it was very interesting. Indeed, it was called the Poisson bracket. And the fact is that all this stuff was described by means of symplectic geometry. So the origins of this is about symplectic geometry. It's about Hamiltonian formulation of the motion of planets. It's about describing differential equations. So what I am going to do now is just to explain how from symplectic geometry we can deal with it. We can somehow relate everything we have in here with Hamiltonian equations. So the thing is that we define here by hand that every function in R to N, okay, well, this could be a manifold, sorry, manifold M with a symplectic structure omega. Okay, let us say this way. All right. The thing is that when you do so, given a 13 function, this defines a unique vector field called Hamiltonian vector field, the function f, defined in this manner. You pick up the function, you pick up the differential. So this is a one form, and it turns out it can be proved that for a symplectic form, the contraction of the symplectic form with a certain vector field always gives us the differential of H. This in here is called the Hamiltonian vector field of H. Is unique because you see, if you had two of them satisfying the same relation, by doing the subtracting them, you would have this, but we said that omega is non-degenerate. That means if two vector fields, the contraction of the difference of these two vectors is equal to 0, this means that it's equal to 0 and both Hamiltonian vector fields are the same. So Hamiltonian vector fields are uniquely defined. It can be proved also that they exist, things like that. And one of the interesting things about Hamiltonian vector fields is that the Lie bracket, the Lie derivative for the symplectic form with respect to the Hamiltonian, and the Hamiltonian vector is equal to 0. So if you write this expression using the margin counter formula, this Lie derivative or the differential of a differential to form of any form can be written like the contraction with the vector field with the differential of omega plus the differential of the contraction with the vector field of omega. But this form, this differential form, is closed by definition, so this disappears. And this thing is such that since xh is Hamiltonian, this part is the differential of a 13 function. So at the very end, you obtain the differential square of a function equal to 0, as you know. This means that the Lie derivative of the symplectic form with respect to a Hamiltonian vector is equal to 0. It lives invariant this. So let us see now what the relation, what does it mean that the vector field is Hamiltonian in 13 canonical coordinates and 13 double coordinates. And we will see that we will notice that integral cubes of Hamiltonian vector field are just solution of the Hamilton equations. And this is the important thing. So pick up 13 function H, pick up 13 double coordinates. So the omega will be like this. Since we have coordinates xi, pi, the differential of the function H can be written in this way. So already this should be the sum equal to n and this 2. Of course, sometimes I wrote, sometimes I didn't. Sorry for that. It will be an okay. To this, you can think about Einstein notation. So the thing is that when you have these, you have 13 vector field and you impose that the contraction with dh, the symplectic form must be dh. By solving the system, you obtain this expression that the Hamiltonian vector field has this shape. And you can see that integral cubes of this vector field, they satisfy that, wait a second. sorry, the minus should be here and plus here. Sorry. Well, it's a matter of calculation, yes. The thing is, the integral Q's of this vector field are such that the of xi of a certain Q must be this coefficient, I mean this, and the differential of pi along Q's must be this expression. And you can recognize that this is just Hamilton equation in classical mechanics. So when you solve this, what you find is that the integral Q's of a Hamiltonian vector field relative to a symplectic structure, they are the solutions of Hamilton equations. Another thing that happens in symplectic geometry is that when you have the symplectic form in this way, you can make the exterior product of the symplectic form with itself n times. So when you do so, what you obtain up to a factor, sorry, this, you will see that when you do the exterior product this with itself, the pair of things, the xi, pi, that are repeated when you make the exterior product, they give 0, and the only elements you get are those that pair that are matching xi and pi with different indices. So at the very end, when you do this n times, what you obtain is something like this, up to a 13th factor. And you can see that this is a volume form. So every symplectic manifold is indeed an orientable one, because this is a volume form, because you see you have all the coordinates. So this is a 2n form on a 2n manifold, and it never vanishes. So it turned out that when you have symplectic form, they all have a volume form, they are all orientable. And it can be proved also, and this one done in the following theorem, that is the Liouville theorem, that the Lie derivative of the symplectic, the volume form associated with the symplectic form is equal to 0. Okay, it does not vary. What does it mean? It means that the volumes are not changed by the flow of Hamiltonian vector fields. So it's fun that if you start here with a certain ball in a certain symplectic manifold, what is going to happen is that after a while, the flow can deform along integral cubes, but you will always have the same volume. Okay, so it can be twisted, it can be changed, but at the very end, the final volume of this thing after a while and the original one must remain the same. Okay, so this is the thing that usually happens with symplectic manifolds, that the flow does not change the volume. It can distort it, can change its shapes, but the volume is always the same. There are many, well, there are many, that's maybe too much saying. There are different results which tells you that depending on the radius of this thing, okay, the biggest radius, for example, this thing is related to the biggest one, which can be found here, or the smaller one they can find. It's called the Gromov theory. So one example of this differential equation described by means of a Hamiltonian vector field is this. When you have these differential equations on the right, the left-hand side, you have a vector field given by this. And you can see that this with omega, if I'm not wrong, okay, will be minus xa differential a. I hope that they write it wrong. Well, this, sorry, this is not p, this is a. Will be the x with a minus 1. Okay. So doing so, you will obtain that this is differential a plus differential x by 2 minus x on the r minus a squared the x. So it will be, just give me a second. this thing. So you see, it turns out that you can here. Okay, it's done. So it turns out that this vector field, this differential equation here, is indeed the differential equation for the integral Q's of a vector field that is Hamiltonian. The contraction to this is this, and this is the Hamiltonian function. Another thing that is interesting is that you have this Hamiltonian vector field. Let's say that this is H. Okay, and you do this. This is the H. But if you do this, as omega is a symplectic form, it gives you 0. But the first contraction is dH contraction H. It is, in this is H equal to 0. And the Hamiltonian function of a certain Hamiltonian vector field is a constant of motion. So this function in this case is something that tells you that your system has a certain integral of motion. And it's quite easy to obtain it. So this is another known result in symplectic geometry, is called the symplectic camel theorem. And it tells you that if you start by 13 times the coordinates for a symplectic manifold, you can define a 13 ball. Okay, you pick up the coordinates around a certain point given by coordinates x0, p0, a moment at p0, and this is just a ball in these coordinates. Okay, so if you have this ball of radius r, and you make the evolution of this ball, okay, it turns out that for every first coordinate, the radius of this is a cylinder where you have the first coordinates are x0, p0, and the remaining ones are whatever. So when you say that among all these coordinates, all are whatever, they are free apart from the previous ones, okay, they are minus or equal to 2. This is describing a certain cylinder with radius r. Okay, so this condition tells you that if you have this ball and you have a symplectomorphism, for example, given by the evolution of the dynamical system, and you can put it inside a certain cylinder with radius r, it turns out that the radius r has to be bigger. Wait a second, I will check. Second. Okay, is this thing. It has to happen. This is other way. Sorry. Okay, it has to happen that this radius must be always bigger than r. That means that this thing cannot be done as small as you can say, okay, as you can wish. And this is related to the biblical passage where it was said that it's more difficult for a rich to enter the heaven than for a camel to go through the hole of a needle. And this inspired to say that this is symplectic camel theory, because it's telling you that if you have a camel, imagine that you have a ball camel with a radius, if you try to put it to pass it through the hole of a needle, that this will be some kind of cylinder, okay, if the cylinder has a radius small enough, you will not be able to put the camel inside of it, okay, because there is a ball. If you can deform symplectically a camel with a radius r and to put it inside of a certain cylinder, the radius of the cylinder must be bigger than the initial radius of the ball. So you cannot put the camel inside a cylinder as small as you want. Take into account that the Liouville theorem tells you that this thing, this camel as a ball, could be stretched. I mean, if it is a ball, you could do such a thing like deforming it into a sausage. Because the Liouville theorem tells you that the only restriction is that the volume of this and the volume of this must be the same. But Gromov thought, okay, so the volume must be the same, but I can make a certain region as thin as I could like. Can I put a certain ball as a sausage as thin as I could want? And the answer is no. If the radius here is r, the radius, what the cylinder must be always bigger than this r. So you cannot do it, and the camel cannot go through the needle. This was the original. But there are lots of results about what Hamiltonian morphisms can do with this thing. So the thing is that with a symplectic manifold, we can define a Lie bracket of functions, okay, of this manner. And the thing is, you pick up omega. For every function f of g, you can define the Hamiltonian vector field of each of them. And when you do it, you can obtain that this is the same as the Hamiltonian vector field of g acting on f. Well, sometimes this is j and h. There are certain changes, okay, in the definition of this. But essentially, this is the way of define a 13 bracket. And this bracket we have defined as antisymmetric because since omega is antisymmetric, when you change the order, it changes the sign. It can be proved also that this is a derivation of each factor. If you pick up this GH as written in here, it turns out that the F acting on the product is the same F acting on H, J acting H, and then H multiplying F at H. So this thing acts a little bit like a derivation, and you have also the Jacobi identity. Due to all these facts, it is said that this bracket is a Poisson bracket. Indeed, this was one of the things that drew Poisson attention while describing the motion of planets, because they allowed to write the equation for the motion of 13 planets in a very easy and elegant manner. Well, there are more properties about this bracket, like, for example, if you pick up the Lie bracket of two Hamiltonian functions with a minus, this would be minus the vector field associated with the Poisson bracket of Fj. So this allows you to tell that if you consider the set space of function of a symplectic manifold with respect to the induced Poisson bracket and the set of Hamiltonian vector fields, sorry, this would be the space of Hamiltonian vector fields with respect to symplectic form, this is a Lie algebra of it. This is very useful. If you write this in coordinates, I will not go with it, you will obtain that the Poisson bracket is something that appears frequently in physics. This is a very well-known expression. A little bit more general is about Poisson manifolds. And the thing is that you saw in symplectic geometry that you can attach every symplectic manifold to a certain Poisson bracket. So the natural question is if out of a Poisson bracket you are always you can be this Poisson bracket related to a symplectic manifold. The thing is, the answer is no, it cannot be. That the only thing can happen is that when you have a 13 Poisson bracket in the space of small functions on a 13 manifold, you can define that there is something called a bivector field. This is at every point is a tensorial product, antisymmetric tensor product of tangent vectors, for example. And this is a bivector field, and this means that you do this. At each point, you make the tensor product of these things with, and you have to symmetricize it. So the thing is, when you have this thing, okay, and you describe this as a contraction, this thing is called a Poisson bivector. I mean, the Poisson bivector induced by the relation is unique. Camille-Plotin is unique, and it's called a Poisson bivector. And the thing is that one wonders, okay, so we have a certain Poisson bracket in here. We have a certain bivector field in here. Which are the properties of this thing? Okay, Poisson bivector. And if somehow given a certain Poisson bivector, I can say if this allows us to define a bracket of functions such a way that this will be a Poisson bracket. So this is done by means of the Cauchy-Legendre bracket. I will not go into details. The only thing is that when the Poisson bracket will be said by means of this bracket is equal to 0, then it turns out that the bivector field gives you a Poisson bracket. So there are certain properties here. Yes, let's go back to the problem we were studying at the very beginning about the problem of Riccati equations and the superposition rule of Riccati equations. Allow me to recall that we have something of this kind. Sorry, this is not free, this is equal to. Let me recall you that we have something of this. We were working out integrals of motion, constant of motion for the following vector fields. Okay, this is the magical thing in here. It turns out that these are things on R4, where you have coordinates x0, x1, x2, x3. Okay, so when I was a PhD student, when I finished my PhD student rather, I came up with the idea that we could define a symplectic form making these vector fields into Hamiltonian vector fields with these Hamiltonian functions, 1, 2, and 3. Okay. So the question that every such a vector field in here on the function we are looking for psi is equal to 0 could be written by means of the Poisson bracket in this manner. Okay, but this is a minus, yes, a convention due to the 13 structures in use. What it is saying to you is that this psi is something that commutes with respect to the Poisson bracket with all the functions hi. And the nice cool thing is that since the functions x1, x2, x3, they span a Lie algebra of vector fields, the diagonal prolongations do also. This is what I proved. And due to symplectic geometry, I proved that the functions too. Okay. So using this relation, I obtained this thing. I write this in this manner. Okay. I didn't know what h1, h3, h2 is. I mean, I didn't use these expressions. I used them just to say that our first Hamiltonian vector fields, this x1 tilde h2 tilde h3, they are Hamiltonian, but I didn't need it much at the beginning. I just wrote it this, and using the structure of the functions, the Hamiltonian functions, I obtained that this thing Poisson commutes with respect to Poisson with the hi. And when I wrote this in coordinates using this expression, I obtained the famous Casimir function. So, out of the blue, obtaining this function that indeed it turns out that it can be found in certain tables is something well known. They obtain for certain Lie algebras of vector fields. I managed to obtain this in 2 minutes. Okay. And to explain geometrically that this is some kind of so-called Casimir related to SL2R or some structure in an instant straightforward manner. Okay. And it turned out that it was a very good thing. It was quite set, and it's now used for many systems because this is pretty useful. I mean, at the beginning we had to solve a system of PDEs, and by means of this, by means of this observation of these functions, and by means of this expression, these so-called Casimir functions that they can be found in books, I obtained the solution of a very non-trivial PDE. And Riccati equation was just the beginning. Okay, this has been used for more than 30 or 40 different systems of differential equations. I mean, it was pretty much used to describe lots of things, and it was used even for quantum groups and for the formation, quantum deformations. It was employed to them so many other systems that are not Lie systems. So let us say this method, this idea was the key to develop several theories and several PhD doctorates. So it was kind of useful. This is another system. This is a trigonometric system. The story is exactly the same. This appears in 13 classical mechanical problems. Yeah. So the story is the same. You start by means of this system of differential equation. You write the time-dependent vector field. You separate the parts with different functions. You pick up the vector fields, and it turns out that they span a Lie algebra vector fields. You obtain the Hamiltonian related functions. In this case, with respect to the standard symplectic structure here, there is not much to say. And the functions you obtain, they close several relations with respect to the Poisson bracket that they are the same as this, but with a minus. This can be explained. And by doing so, we obtain also a superposition rule for this. It can be done. And well, this what it follows is just a development about, well, this works and works and works, and the Poisson, the coalgebra method with, well, this is an example with Kumerer-Bar's equations. This is for the real. There are lots and lots of examples, and it can be generalized to many structures. This is for Dirac manifolds, the so-called Dirac manifolds. What else I wrote here, because it must be multisymplectic structures. Also, it's exactly the same with different examples, but the fundamental idea is exactly the same. This is what this is the last thing I did. I think that it was a content manifold. And I don't know, this is a story that never ends. This is for a control system. Well, truly speaking, as I said, this can be much generalized. There are a lot of structures for which they can be done. They have been published in many good journals. Some of them, they are one of the best of the world. In a couple of cases, not much, but well, sometimes we manage. It has been the topic of, related to the topic of certain PhD dissertations. Let us say that I hope that it was interesting. I will finish here. This is the end. I mean, this is what I was supposed to show you. More detail, if someone wants, I can send the slides. And thank you very much for your attention.
Thank you, Javi, for this talk and this nice course. Are there any questions or comments? Looks like there are no questions. Okay, no questions then. Any comments, Javi? You want to do some remark?
Oh, there's not much to say today. I guess that I said already a lot of things about it. The only thing is that, well, it is possible to make many advances in this. It is an interesting topic for many people, and it's a way of learning differential geometric while doing integrable systems and doing interesting stuff. That's all. I think that is nothing else to say.
Okay, so thank you again, Javi. And next week we will have Adam, who will talk about category theory and things like that, if I'm not mistaken. Okay, so thank you all for attending and see you next week.
Thank you.
Thank you.